So today, it's database models. Got one little thing. One of you tried to use VirtualBox and the VM on the library computer. Yeah, yeah. I have been in contact with the library and IT services. Unfortunately, as the library laptops are set up, it's not going to work. So I've asked them to fix it, and they sort of, we'll wait and see, is the bottom line. So the bottom line is, unfortunately, you can't use the library computers. Now, if that's a real problem, in that you came here expecting to be able to use that facility and it's severely impacting on your life, maybe we can go back to them and say, look, people are really desperate here. So bear that in mind. So the library computers, if you don't know already, there's laptops that you can book out, but unfortunately, it won't run the software that we want. Okay, so I put in a request, so it's on their list of things to do, but let's not hold up. Yes? No, it's not nothing to do with the main computers, it's just the laptops. The laptops, basically you use the laptop and then you see it sign into My Desktop Anywhere. Are you all familiar with My Desktop Anywhere? Yep. No, My Desktop Anywhere allows you to log into your university account and have the university Windows and software system running within a virtual environment on your laptop. So you can log in, get your email, get just your normal KU, start menu, everything else, all the programs and everything like that. It's fine for things like Word and accessing your H drive and possibly running SPSS. Running ArcGIS through it is a bit of a nightmare, though, and is not to be recommended. It's possible, but expect it to fall over, expect trouble. So your ArcGIS, as you may know, or are coming to learn at a rapid rate of knots, is a very large program. It's rather temperamental, and it's almost always used locally as a local install on a computer, and not to have your data on the network drive. Okay. I don't know if in other modules, if you're being told to store and use data on the H drive and work with data on your H drive, you are being given incorrect instructions. Tell me who is telling you, giving me that information, and I will go and have a word with that dark alley. Okay, so yeah, software issues. If you've got a problem, come talk to us and we'll try and get you a workflow or a system whereby it works for you. Okay, database model. So this is something I was going to, at the end of last week's lecture, I say, I'm not worrying about whether I go over or I'm doing on the various sections. So last week we talked in the sort of second half about Ackoff's model of translating from data, base data, the base items of information that we have, the facts that we record, how we extract it, put those together to make information, put it together into greater constructs or conceptual constructs for knowledge, and then hopefully we can use our knowledge wisely to make productive things, make productive decisions. Here's another part from Ackoff's original paper. We don't know where these figures come from. I suspect he licked his finger, stuck it in the wind and used his expert guidance rather than being strict figures. But I think they're sort of, their figures and the whole concept rings true, even though they may not be backed by quantitative figures. It'd be great if anybody could find some quantitative figures for these. But within many organisations, this tends to be the case. A lot of the effort goes into capturing the raw data in the first place. So my first GIS job was mapping the water mains in Edinburgh. And there were quite a lot of us in the drawing office, and we spent our lives driving around the city in yellow vans with wheels, measuring where valves were and tracing the old maps and stuff like that. So there was a lot of effort brought into the capture of the raw data in the field. then that data has to be looked after, has to be stored, has to be cleaned, has to be looked after into a database, and the information queries done on the database to extract information. Fewer people are involved in that. There is a bit less effort involved. There's a bit less manpower. You could say person hours, person effort. Then, as you go up higher up the structure, those people, the decision makers, the managers, who are using the information extracted from the databases, making decisions. In the case of a water company, are we going to build a new water main? Do we need to upgrade the pipes in this area? Have we got hydraulic flow problems? A smaller number of people were involved in sort of analysing those sort of larger scale problems. And then at the top, there were the people, the managers, the higher managers who said, okay, we're going to spend £3 million on upgrading this water supply system in this way. So basically, you've got the biggest effort comes in at the bottom with managing the data. Then as you go higher up the knowledge pyramid, less effort is required from people. And I think I did show this slide briefly. The role of what information technology systems do, and particularly databases, is do the heavy lifting at this bottom end, where at the moment the most human effort is required. So good information systems should help reduce the effort, the person effort required at these lower levels, preferably raising the time that people now have the ability to work at a higher level than they would have otherwise if they weren't mired in the basic mechanics of looking at our capturing and looking after the data. So, going to this 2 hours, and I hope we get through it, I'll probably have to go quite fast, is going to cover an introduction to database model. Then, in more depth, look at the relational database model, and finally a small section on spatial databases, their relationship to other database models. So that's the basic overview. So we'll start off with database models. It's easy to put a square into a round hole. All you have to do is cut every single corner and cram it in as hard as you can. So this slide is there to say there are lots of different database models, and we're going to see some of them in this, quite a lot of them in this first section. In theory, in practice, you can take any data and store it in any database model. It's not that you can't do it, it's whether you should do it, and is it the appropriate model to store the data in. And that is a design decision. Okay. So you could have video, you could store it in a relational database. You've got video, you could store it in an object database. You've got video, you could store it in some NoSQL database. I'll just explain what these things are in here. That's what the first section's about. But one method is probably more sensible than the other method. So, in the beginning, there were flat files. And what do I mean by a flat file? Flat files are basically raw, we say, text files. They could be binary as well, but they're generally regarded as text. So here, here we have a text editor called Notepad++, which is, if you're familiar with Notepad in Windows, it's just basic text editor. And I'll talk a little bit about what text is, but here we have some information in just a text document. Now, a text document, what is a raw text file? Well, that's actually a sort of easy and a difficult question to answer. So, text in a computer is everything that is ultimately stored as ones and zeros in the computer. And what various file formats and programs do is take those ones and zeros and interpret them in some fashion. And what we call raw text is where those ones and zeros simply represent the basic numbers and characters of the Latin alphabet. I think it's the Latin alphabet anyway. So we can see your standard characters, your basic characters. There's no accented characters in here. There's no Chinese characters. There's no other characters. Generally, it's they're stored very simply. There's a simple mapping between the zeros and ones on the disk and the characters that appear in your text. Now, when I say it can also be more complicated, is that there are different ways in which these are encoded on disk. So you may hear of ANSI, American National something standard for text. You may see of other standards, which are how you translate the individual characters into the bits on the disk. But basically, think of raw text as numbers and characters without any formatting or anything like that. So no highlighting, no bold, nothing like that, which you have in a Word document, a word processing document. It's just simply text characters, in this case, would anybody like to guess what that text is defining, what it's about? No? Projection, yes, it's a definition. It is a definition file for the WGS 84 projection used by satellite GPS positions, the US satellite system. So that is the definition of the WGS projection steroid, okay, in the text. Here we have a tabular table of information. We've got 3 fields, 1 ID, 1 name, and 1 team. And this is called an example of a delineated text file that stores data. And we have 1 bit of information followed by a tab character. If you're familiar with tab characters, it's that one with the sort of left and right arrows on the right-hand side, followed by another list, followed by another. Okay? So these are 2 different examples of text files. So in the beginning, we call them text files or flat files. They're called flat because they just exist as a stream of characters and there's no interconnections in the file itself between the entries in the various lines and between different files. Not directly, not inherently in the files. They may be in the structure of the data that the file information describes, but not actually physically encoded in the files. So we can store data in flat files. We saw 2 examples of types of data, one a projection definition and the other one a table. Sorry about this, we've got some problem with this. And we could store, and people do store, all their data and information in flat files. This is how computing started. Before we invented database software was invented, that's what everybody did, that's what you had to do. And of course, in days gone by, before it was flat files, it was punch cards and things like that. But this is an inefficient way of doing things. It's ad hoc. Every system will have its own set of flat files. Perhaps in one system, your tables are tab delineated, but somebody else has done comma delineation. Somebody else has used semicolons. So there are lots of different ways that these are formatted. There are lots of different ways that we could format that project definition. The same information could be stored, but arranged in a slightly different way in the text file. So everybody starts doing things in a different way, ad hoc solutions. There is also potential for the duplication of information across files because there's no what we call semantics. Semantics is knowledge, information embedded in the data. So, for example, we might have 2 tables of similar data, but we might have rows information repeated across those 2 files, but because there's no connection between those items of information, we end up with duplication, we end up with also drift, because if we edit one version of that information but don't update the other version, then we've got two slightly different versions of the same information. So we get duplication and gradual kind of erosion of the information content, splits between the duplicate information, they start to diverge. Flat files are, well, you can edit them in a text editor like that, and if you've got 10 lines of in a table, that's great, but if you've got 1 million lines in a table or 10 million lines in a table, it becomes more and more problematic to actually manipulate the data in a text file. Just simply loading it into the text editor and viewing it is hard enough by the time you're into gigabyte type files that we're starting to get with large big data systems nowadays. So there's real problems about file size. They're very inefficient. Because they're so general, they're very inefficient in data storage. They are files, and as such, they are subject to single user locks within the computer. So, say we have a system of text files that store our information, and I've decided to edit some data in one of them. My colleague wants to also edit data in that file. They can't do it because it's locked out. So you can only have one person doing anything to a data file. Well, anybody writing to a data file or locking out a data file at any particular time. So you've got problems of multi-user access. Because the data, these are ad hoc systems, and then store the data, arrangements of the information, and then applications are built on top of these. Because the system that stores the data differs between all the systems, what you effectively do is get closely linked applications and data storage systems. Okay, so you build a data storage system, you build an application on top of that, and those two are so closely linked because the application requires a particular format, the data to be stored in a particular format, and vice versa. So they're very closely linked. Applications and data are very closely connected. As we'll see later on, what we want to do is to separate applications from data, and that gives us far more flexibility in what we can do. And because of the complexity of it all, it required took a lot of effort and time to both manage the data in these flat files and the systems, develop the systems that then access the data in those files. So they work, it's possible to do. Lots of basic software systems still run on flat files. There's nothing wrong with flat files. Well, there are things wrong with flat files, but under certain circumstances, flat files are a good solution and remain to be so. And flat files are used throughout computing. So it's not like flat files aren't any use, but they have their limitations. So, flat files were a problem. So people started thinking, how do we can do better? And the solution is databases. So what is a database? A definition is simply an integrated set of data on a particular subject, usually held digitally. That's a general sort of definition for a database. So a database, it used to be, before computers were widely spread, databases would be on card systems. When I started working, it was mostly on handwritten card systems. And it was only sort of really in the 80s that many big organisations like councils, utility companies moved from paper-based systems into digitally based systems. So databases can exist on paper, they can be manual, but really we're talking about digital systems nowadays. A database, data in a database is structured, organised, arranged, following some kind of database model. And that's what we're going to meet in a minute, that's the different database models. Data within a database, we often describe with, or we should describe with what we call metadata, which is data about the data that we've got. And we've got a whole lecture and half a lecture on metadata in due course. So there's not only the data itself, how hot is it outside now, but there's the metadata that goes with that. How often is that information connected? What instruments did you use to collect that information? Is it a manually read thermometer? Is it a digital temperature probe, etc., etc.? And importantly, databases support the querying of the data they contain, and that querying can be done in a whole variety of ways, or through a different number of different interfaces. The two that we're going to be particularly interested in, frankly, these are the two ways, is either directly through writing queries in a query language, SQL, or SQL. I've got to change from saying SQL to SQL, which is the correct pronunciation of it, but it is stuck in my brain as SQL. So SQL, which is the standard query language for relational databases, and that's what we do next week. The other way is through not generic or custom graphic interfaces. So using ArcGIS interface to do an attribute query on a table would be an example of using a generic interface, a generic GIS interface to undertake a query. So these are sort of the negation of some of the things that were bad with flat files. Pause while the screen does its thing. Sorry about this. There's this thing going down. Okay, system is restarting. I'm going to complain about this. I did it last week as well. Wish I had a short pause. How was this morning? Are you doing statistics? Yet? No? Sorry? You did it last. So those of you who are doing it, did you do your statistics? This is Nigel this morning. Is that right? Sorry? Not statistics yet. Okay. Right. Let's go back to our laptop. HMDI. They probably set it because they think no teaching goes on a Wednesday afternoon, so they set it to reboot on a Wednesday afternoon. Right, okay, so advantages of the database. We had the redundancy problem, or the data duplication problem was mentioned. In database terminology, that's called data redundancy, duplication, because you've got redundant data. The copy of an item of information is a redundant element in your system. So databases help us avoid duplication, redundancy of data. They help us separate the data processing from the applications that we use to query the data itself. So we can have lots of different types of applications for different groups of users accessing the same information source. They're designed to support multi-user access. So if two of us try to update the same bit of information at the same time, the database can handle it. It might just flag it up as a conflict or something like that, but it supports multi-user access to the data. They support, I've already done this, multiple concurrent applications. So you could have one database running here, and you could have a web app, you could have customers accessing that database through a web interface, then you could have your super user analysts in your company accessing it through QGIS or a ArcGIS onto the same database. You're all accessing the same database, but you're using different applications for different purposes onto that data. It helps us enforce standards, data standards, how to enter information, so that that's another way of stopping our data drifting. So if we've got, for example, we want to define something as public or private, rather than having somebody type public or private, we have a pull-down list that enters those values. They're always written in the correct case. Everything remains consistent. They enforce security, who can access what bits of information in the system. And because of the tools and all the things, the above things, the things above, it reduces development costs and maintenance costs for the entire system. So there are financial benefits as well. There are some disadvantages of databases, though. One is simply the setup cost and time and skills, time and cost in developing a database. If you've got one table or two tables that effectively don't change and are relatively too easy to manage in a spreadsheet, why bother putting them in a database? There isn't a reason. Well, there may be a reason, but the fact that the data itself is not a reason for putting it into the database. You could maybe manage the system quite happily with Excel and some tab delineated files that you read into your applications on demand. There's no reason. That's, again, it depends on what the needs are of the users of the system. Some data is really complex to structure. There are complex data sets out there. So there are sometimes, if you've got some complex data structures, sometimes flat files are basically easier to do than developing a complex database model in which to store this information. So some data doesn't fit well, or it's more difficult to fit into the system. You need additional software to access the data, whereas for reading text files, it's dead easy programmatically to read text files. You could learn to do it in half an hour or something like that. Read the basic information out of a text file. Accessing data in a database requires database drivers and things like that, which are generally available, but they do add a certain level of programmatic complexity on top of the system. Performance. Well, tuned databases can be extremely efficient at extracting data out of the database system. However, very large data, this is going back to our round peg square hole, certain database systems and database models are specifically tuned for dealing with high volumes of data. Other ones are particularly suitable for dealing with high complexity in data. So if you're using the standard relational model with highly complex data that involve multiple tables being put together to provide the answer, it can actually be quite slow. So there are issues of slowness and speed as well. So history, a history lesson. So this is kind of a classic historical timeline of database models. Beginning in the 1960s, and we're presently in the 2000 and whatever we are, 16 now. So we start in the 1960s, and I'll go through each of one of these, well, similar. We'll go through this historical process with a number of slides after this one, but we start off in the 1960s with the first databases, which use the hierarchical data model. I'll explain that in due course. Then the network data model came along. Then in the 1970s, the relational model turns up. The relational model is currently, I would say, definitely the widest used database model in the world, and probably has up to 75–80% of the market globally. The other database models are filling up the other 20–25%, something like that. Then in the 1980s, we start to go, or 80s, we start to enter object-orientated database models start to appear, and then in the 2000s, we've got an expansion of systems which come under the NoSQL banner. NoSQL is the standard query language for relational databases. NoSQL is sort of saying that this is a database that doesn't use SQL, isn't relational. And as we'll see, a lot of these NoSQL databases are modern versions of these hierarchical network databases that originated in the 1960s. In general, as we take this timeline through, there is an increase, a trend for increasingly increased semantics. Remember, I mentioned that semantics, and that means adding meaning into the data itself. So there's knowing that there's storing a value, say, of saying it's 17 degrees centigrade at 3 o'clock in the afternoon on a certain date. That is what we could call, that's the actual data itself. The semantics is sort of knowing that that is temperature and what you can do with temperature and what temperature means. So we'll get onto that in due course. That's a lot later in the module. So basically there's a trend to develop more and more complex systems that are able to manage more and more complicated data sets. There has also been other pressures, particularly by the time we get to NoSQL, which is the arrival of what we call big data. Very, very large data sets from remote sensing, satellite imagery, from automatic sensors, from census data, from the stuff that Google do, those of us with Android phones, every time we walk around the place, Google is monitoring where we are and working out how fast we are moving, and that's how they produce the Google traffic layers that you can see and use for navigating. So they are dealing with petabytes of information, which requires advanced database technologies to manage. Yeah, there we go. 21st century challenges. So we've got data, we've got large data volumes, we've got increasingly complex, heterogeneous, meaning different, made of different bits, data structures. So in my work, some of my past work, I've had range maps, evolutionary trees of mammals, trait database of mammals, food webs of mammals, and we're trying to put all this heterogeneous, these networks, these trees, these spatial data sets, these more traditional attribute tables into a single database environment in which we can query across these different types of data sets. There's unstructured data. What do I mean by unstructured data? Well, things like the information in papers. So in documents, that's what we call unstructured data. Structured data is data in nice little columns and lists and things like that. Unstructured is stuff information spread among text rather than formatted into tables and things like that. Different ontologies. What's an ontology? An ontology is the way you classify things, the way we break the world into parts and components. And I think I mentioned this before, so we all have a different view over what a tree is, for example. And maybe the council's view of a tree is not the same as an ecologist's view of a tree. We have different words we use different words to describe trees. We have different needs and information needs in respect of trees. So different ontology means if we're interested in mapping the management of urban green infrastructure, the trees and things, and we're also integrating that and we want to understand it from bringing information from, say, ecology data information systems, we've got to get them to talk the same language, because one world is the world of landscape management has one set of vocabulary, and the world of ecology has a different set of vocabulary. So we have to learn to bridge these vocabularies into language, disciplinary languages. We've got data in lots of different places. So it's supplied by different people with different rules for use, different licenses for use. So how do we integrate these data together and don't break the rules of data usage, the laws of data usage? Once we release data out into the wild, into the internet, so we put it up online, and suddenly you've got loads of people downloading it. And then you've got people adding new information to it because perhaps they know something additional that you didn't know in your data set. So we suddenly end up with multiple versions of the same data set spread across the user community. And that's not just people updating the data sets, but for example, you might have release a version every year, or it may be periodically updated. Somebody's using the 2005 version, and somebody else is using the 2003 version. How do you match those two together? How do you track those changes? So we've got duplications of data sets out in the grand world. We've got different sets of user communities want to accessing the different data sets, and the skill base and levels of those different user groups are going to vary greatly. So for example, you may have professional information scientists trying to access a data set. You also maybe have citizen scientists interested in that data as well, and that data has to be made available for all relevant user groups. And then there are the challenge of critical services, critical systems in the 21st century. If eBay went down, how much profit does eBay lose per second if their system is down? They want multiple versions. They need robust commercial systems. We're thinking about things like defence systems. You want a system that's tolerant to potentially attack of various kinds. So we need robust computer systems for critical service. The hierarchical database. So we go back to the 1960s. Now this is going to be very superficial, I hasten to add. I am not an expert on the pros and cons of hierarchical databases, but we're going to run through the basics of it here. So hierarchical databases were the first digital databases, basically go back to the early 1960s, and basically the records in the database are organised into a tree, a hierarchical tree. So here we've got it's actually a spatial example. We have a map at the top, a map object or map record. Then we've got, within the map, we've got 3 counties. Each county manages the roads in the county. So County A has road 1, road 2, road 3. County B has road 4, road 5, road 6, and so on. So if we want to know the roads in County A, we go from the map to the county to get the roads. If we want to know which county a road is, we go from the road to the county to the map. Nice, easy data structure. And that's, it's got some advantages. It's particularly good at rapid access and updating of records, particularly tip records. Read down the bottom. Because all you do is add another one in or delete this one. So that works well. But when you start adding and removing records inside the hierarchy, suddenly if we deleted County A, we have a whole load of roads with no county. We can't do that. We physically can't do that because it has to be a tree structure. And you can't have records that are floating around and are not connected to the tree. So you have to rebuild the tree. So if you're taking off these internal nodes, you have to rebuild the tree every time that you edit a record, remove or add a new record, delete a record. That takes effort and time. So it's all right at the tips, it's not so good at the internal nodes. So if all you're doing is ever adding more tips and deleting more tips, it's a good data model. But if the structure underneath those tips has to change, it's not a good data model. It's a problematic data model. It's also very limited, as you've probably seen, that each record can only have one parent record. So each child can only have one parent. Parents can have many children, but not the other way around. So, for example, what happens if road 3, in fact, crosses the border within both counties? You would have to have a duplicated record of road 3 over here. There's a lot of different ways we could do it. But we can't just have road 3 and then have a link across to county B, which would be a nice solution, no duplication of data. Remember, data redundancy is one of our great no-nos. We keep away from it wherever possible, we avoid it. Also, the databases in the 1960s, the hierarchical databases, they were all different. They were all built by different companies. They didn't share any generic query language, so no common language for querying these things. You have to learn each database model. You have to remember the particular language for each, or learn the particular way to query each of those structures. Hierarchical databases were used by the Apollo 11 moon landing. This is one of the early classic applications of it, to manage the components for building the Saturn V rocket that took Neil Armstrong and others to the moon. So, it had a huge benefit in the 1960s. And it's still, that same database project, IBM IMS, is still on sale in 48 years later, after Neil walked on the moon. It's still available for purchase off the IBM site, and it is used particularly, so the example one of the ones that they have on the main website is that I think it's the National African Bank or something is using it for its mobile banking applications in South Africa, because it's particularly good for these rapid tip adding, deleting records, changing records at the tips of these trees. So it still has real world applications in particular areas. Mid-60s, the network data model has its limitations, and one of the main ones was this inability to cross-reference records so that child records could only have one pair of records. The network database model came along in the mid-60s and allowed these now supported these cross-links between these data sets, so we got rid of one of the problems of duplication. But we've still got this problem of adding and removing intermediate records results in restructuring of the database. Having to restructure the whole structure of the database. County B is deleted, we've got to rebuild the network structure between the records. Also, particularly in the 1960s, not so much now, with the increases of computer power following Moore's law. If you know Moore's law it's not a law, it's an empirical observation that processing power doubles every year. So we've got a massive increase in computing power. But in the 1960s, processing power was extremely limited, and they could only store and model small numbers of connections between nodes, so you were limited by the computing power at the time. We'll meet these again in due course. Here's an example of a graph database today. Graph databases are really taking off again now. It's a really interesting area. Neo4j, have a look at their website, see what they're doing, is one of the main players in the resurgence of network databases. One thing that I know it's been used for is, well, it's not relevant to geography, is something called the Open Tree of Life, which is an attempt to take all the evolutionary trees and network models that have been generated by analysis of DNA of organisms and turn them into a giant network model of the relationship between every organism on the planet. So that's an example of big data science using Neo4j today. Okay, trundling along to the 1970s. And a new database model was developed by Edward Codd at IBM in Menlo Park in California, where he works at IBM, International Business Machines. This was why did he develop the relational model? Well, the limitations of the network and the hierarchical model in particular, the lack of genericness of it. The fact that you had to develop these things for particular problems to address particular data sets. Whereas the relational model that he developed is what we call a generic model that can be applied to many different situations. And it's quite a simple model. The data is stored as records, rows, in what's called a relation, which is a fancy name for a table. Why is it called relation? It's because relational databases work on the underlying principle is relational algebra, predicate logic, and it's called relational algebra. So it comes from the process of combining information across tables. That's where the word relational comes from. And why we say it's a relation and not a table. The reality is that table and relation are pretty much used interchangeably in the literature. And if you're reading a more database information technology related article or book, it'll probably call it a relation. But if you're reading a more general usage book, it's going to be called a table. So bear in mind the different terminology. And the data that is stored in separate tables is brought together by joining, the process of what we call joining. Relations using key attributes and relational logic. What does that mean? Okay, well, we'll see that in a sec. Quick little tour, is relation table terminology. Now we're going to revisit this in the second half of the lecture when we look in the relational database and modelling more generally. But here's the terminology of a relation or a table. Here's our table, our relationship. We've got each column contains as a name and defines what kind of information is stored in that column. Each row or record stores an instance of that, whatever it is being stored in the table. So here we've got postcodes and the population in postcodes. So we have one called the name of the field. These columns are sometimes called fields, sometimes called columns, sometimes called properties or attributes. So again, the terminology varies, but they store equivalent values about the same subject. So in this case, the one called sect ID for some reason, section ID. Why didn't they call it postcode ID? I don't know. But these are postcode sectors, I think that's what it's called, sector. So KT25, KT27, KT26. KT postcode is the Kingston postcode area. And then each row, so for each of those, we have the number of households and then the numbers of various groups and things like that. So information about postcodes goes all in the column here, information on how many households there are goes in this column, households, and information about the postcode goes directly to the postcode number. Well, that's a table. You know what a table is. I mentioned keys before. What's a key? Well, we're going to see keys in more detail in due course. But a key field is just a field or a set of fields that uniquely identifies a row. Okay, so that's a relation. What do I mean by joining relations? Here's a sort of schematic example of joining a relation. So I've got two tables. One table is on the counties, and this is the population of each county. The other tells me counties and which roads are in each county. I want to know, return the joint information. I want to know for each county what the population is, how many roads there are, and how many roads there are per population, 1,000 population in this case. So, county, this table has a field called county, A, B, C, each county has a population. This table tells us which roads are in which county. So road 1 is in county A, road 2 is in county A, road 3 is in county A, etc., etc. So what we can do is we can take, in joining, is we take the key fields, which should be, in fact, this one is pointing correctly, it should be a county. So we're taking for each county, we go and grab the records for the county, for that county over here. We can count how many records there are, in this case there are 3 for A, so road count is 3, and then we can get the population from this table, so we get the population from this table, we match them from the county ID to get the number of roads, and then we can divide the population by the number of roads within our field. So here we're combining information that's spread across 2 tables. That's the process of joining. And that's the sort of crux of the relational model. Data and tables joined between tables. So relational model is most commonly used. Why is it commonly used? Well, it's a single standardized data model. So you take a relational model off the shelf and you can apply it in lots of different areas. It's a really generic system. You can apply it in conservation management applications, in utility companies for managing customers, etc., etc. It supports, there are lots of community standards for how it's done. So there are standard ways of defining a query language, standard ways of arranging data and organising the data into the database. So it's all nicely standardised. There are many software implementations of relational database management systems. A management system, that's a piece of software. So there's the model, the relational model, and then there's the software that implements the relational model. So there's many different types of software examples that you can use, and we'll meet some of them later. But remember, not all data is optimally tabular. So things like spatial data is not tabular. It doesn't fit well into a tabular system. We'll deal with that in due course. Free text, it doesn't fit very well into a tabular system. So documents don't fit in very well. Images, You can store an image in a relational database, but how do you analyze it? Same with movies, videos, sound files. They're not very good at hierarchical data, where the relationships are into hierarchies or networks. They're no good for that kind of stuff, or not very good for that sort of stuff. And as the data sets become more complex in the relationships between the various data items, you get a more and more complex relational model is required to store that complexity, and it gets to the state where it's actually difficult for us as human beings to comprehend the complexity of the links between the various tables. It becomes difficult to actually store that in your head and get a full picture about what's going on. It becomes so complicated. And also, as it becomes more complicated, more and more tables are required, more and more joins are required, complex joins are required. Things get slower and slower and performance goes down. Okay, quickly. 1980. So we've got a problem with complexity. So this is where the object model came in. The object model was developed in the mid-80s, probably dates back a little longer than that, but started to become of age in the 1980s. It was the brave new world when I was starting on my GIS career. It's not quite the brave new world that it was intended to be or seemed to be in the 1980s anymore. But that's to say the object model has become a really important model, not so much from databasing perspective, although it is used in databases, but from programming perspective. So when we start to learn Java, we're going to be using objects a lot, thinking in object ways, and we do our JavaScript programming later on. Conceptually, the object model works, and we'll have a whole lecture on the object model later in the course, is that we identify the objects, the entities that exist in the world. Peoples, cars, trees, water pipes, valves, all these things. And that all these things in the world, these classes of things in the world, have attributes. Well, we know what attributes are. The car is green. The car has 4 wheels. The car is a Ford or something like that. Set of attributes. But they also have a set of, the objects are related to each other in various ways. And they're often can be arranged into what we call class relationships or class hierarchies. So here's an example of a hierarchy on the right-hand side. So this is a this is a bibliographic, a library-based system example of it. So we've got something in our library catalogue. So we've got things that are in the catalogue. There are different types of things in the catalogue that have different attributes. So, for example, a book has a different set of attributes than, say, a serial. A serial being something that's published on a periodic basis. And then there are different types of serials. So, for example, there might be academic journals, and then there might be more magazine-type things that haven't gone through some peer review process and things like that. But basically, we can say that a magazine shares all the attributes and behaviours of a catalogue item because it's part of the catalogue, but it also has its additional things that are special to being a magazine or a journal. So we have these types of relationships, which allows us to model, so we can model and these allow us to model the commonalities between journals, serials, books, and catalogue. So don't worry about the details, we'll come into that in due course. The other type of important relationships that are modelled are things like part-of relationships. So a car has an engine, it has 4 wheels, the engine has a, I'm lost at this point, it has engines, but what goes on in the engine, I have no idea. What goes on, it has pistons and it has spark plugs and things like that. Things I pay people to deal with. So we have part-of relationships like that. And we can see that we can, from these relationships, we can build a sort of more intuitive model of what these objects are. The final thing that objects have is that they have behaviour. They have things that they can do or can be done to them. So, for example, an object might be able to return some attribute about itself. It may be able to calculate some kind of statistics on the basis of that object, something like that. Now we're going to go into the object model in more detail. Of course, here's just a sort of conceptual view. It's very hard. When I was learning about object models, I really had a difficulty picturing what it all meant in my head. So this is my attempt to provide a picture for you as to what the object model is and what its benefits is. So here's a cat, the class cat. The class definition, we have a class definition. We need to define what a cat is. And the class definition provides us a template for storing information about cats. So, for example, the attributes we might have for our cat are name, weight, and colour. Are the three attributes of a cat. What does a cat do? Well, behaviours. It does things like eat, sleep, purr. My one likes producing hairballs. It's his speciality. So it might do things like that. Also, as we think of a cat, we think about modelling a cat. Well, the things I've said here are mostly about the whole cat. But we can divide a cat and create a class hierarchy of a cat. So a cat has a head, and the head is a part of the cat, and the ear is the part of the head. So we can start creating a much more complex model of what a cat is. And the ear maybe can waggle, or the head can bite, but the body can't bite. So you've got different attributes spread across these different parts of the organism in this case. When it comes to recording information about a particular cat, what we do is we create from this template, we say generate, turn the handle, kick out an empty cat record, and then we can start filling in these attributes for the individual cat. And each individual cat will have a unique identifier. So every instance of a cat has a particular special number attached to it, and then we can add the values for that cat. Okay, so that's an example of class. What does it do? What does it make? How does it make life easy? So here's our relational cat. In our relational cat, we store the attributes for each body part in a separate table. So, for example, we might have a leg, and we might want to know the length of each leg. After all, they all are slightly different. For example, they may vary by colour. So we might want a colour attribute for each leg. And say we wanted to know all the information about the head of the cat. How do we get it in a relational table? Well, we have to actually know which tables make up the cat head. So we would have to know that we need the information about the cranium, the nose, the mouth, the eye, the ears, the whiskers, from the whole information we've got about the cat. We need to know what a head is. In the relational model, because of the hierarchical part of structure, all we need to do is, which already includes that information, it knows, it's embedded within that hierarchical structure what the head is, because of the part of relationships. All we have to do is select cat.head. So this, you can see, is a much simpler way, more intuitive way of getting to a cat's head than this. Object databases, they exist, they're out there, but they tend to run, I've never used an object database in 25 plus years I've been in GIS. Never ever used one. They tend to be used particularly for things like complex systems like airline booking systems quite often use object databases. But objects, as I say, have become, they maybe have 15% of the market, I think, roughly, the figures I've seen. So, okay, right, last one, just before we have a break, no SQL. So along came the 2000s, the millennium came along. Unlike the predicted bugs, millennium bugs, all the computer systems didn't break down, only one or two broke down, which is quite amazing, I thought. So one of the other things is we're moving into this area of big data. Suddenly computing has stopped being something that's either done by experts in mainframes, in basements, and it's moved out onto the desktop. And now we're in a world of very large data volumes being collected, and as I say, also this issue of heterogeneity, the fact that we're trying to bring different information sources together and be able to interact between them. And as a result, there has been an explosion or radiation in terms of database models to address the primary problem of complexity and data volume. And a number of different database models have been produced as a result. Simple ones, key value pairs. I'm not going to go into what these databases are. Read an introduction to NoSQL. Basically, simple mappings between a key and value. Column family databases, so these are used by, I believe, Bigtable, which underlies Google search engine, things like that. These are the sort of data models. We've already seen Neo4j, the resurgence of graph models, the resurgence of hierarchical database models, but or what are called now, rather than hierarchical models, they're often called document models. So to a certain extent, this is just a revitalization of the old hierarchical graph-based models, but also with some other new concepts involved. As I say, these different data models, these new data models, and we'll touch on some of them, particularly the graph model, much later towards the end of the course, are dealing with the problems of either scalability, very, very large amounts of data, and how you sift through billions of records potentially in microseconds, because if Google search engine doesn't return you in a fraction of a second, you're off to bin or somewhere, maybe. Certainly if it takes any longer than about a second, your usage of Google search engine is going to go down. So these are key value pair sores and column families are particularly aimed at very, very large data sets, whereas document databases and graph databases are about complexity and dealing with the complexity of data sets. So you've got a trade-off between scalability and complexity in these modern NoSQL databases. I won't go look at that slide, but that's sort of showing, each one of these colours is showing the different types of relationships between records that these different database models can store. And what I think I want you to sort of take away from this is that we're moving from a situation where you've got this sort of, the relational model has been dominant for so long, for 30 odd years, but that bastion, the walls of that bastion are starting to break down. You started off with the object models taking over some of the complexity, the problems with complexity. Now you've got other NoSQL databases dealing with the large data volume problem. The relational model, as far as I can see, is going to stay pretty core, I suspect, for a long time yet, but there are these new, and you can almost customize these. You can almost build your own data model using, you can take these things, these are just sort of becoming more and more complex versions of starting off with a really simple key value. So this is these different values. So we won't go into that. Okay, let's take a quick break. Do you want 10 or is 5 sufficient? Probably want 10 if you're going to get a cup of tea. Okay, quarter past. I won't worry unduly if we don't finish off, and I'll have to do a little bit next week.